Okay, so these are the class notes for section 8.3. We're going to go into how we figure out molecular shape, how we figure out symmetry, how we figure out polarity. We're going to do all of that. The polarity is going to come more in section 8.4. So this section of notes is going to help us complete columns 3 and 4 of our shape slab, which is just shape, molecular shape, and molecular symmetry. Okay, so we're going to start over here. So hopefully you've already completed this section using the book, and there are just little pieces that we're going to add in here. So first of all, sigma is, the Greek letter sigma looks a little bit like this, like a sideways number 9. So if you wanted to fill that in, pi, we've been using in math, so we can go ahead and fill in your symbol for pi. Usually people have more of a curly top to that. But sigma and pi bonds, basically, we're looking at sigma bonds. They're symmetrical around the entire axis, and that makes them very strong because there's a lot of overlap there, okay? But pi bonds, the definition in the book wasn't amazing, but they're kind of just the opposite of sigma. They are not symmetrical around the axis. So if you want to just add this, not symmetrical around the bond axis, not symmetrical around the bond axis, and that gives them less overlap and makes them a little bit weaker. And so in this box here, strength of sigma versus pi bonds, we just want to know pi bonds are weaker. They don't overlap as much as sigma bonds. Okay, so when you have symmetry, you get more overlap, you get more sharing of those electrons, and that makes a stronger bond. Okay, now the majority of my class notes today are going to be on this Vesper theory. Okay, Vesper is our dyslexic way of saying VSEPR, and valence shell electron pair repulsion is what that stands for. And really, that tells you what it's for, right? Valence shell electrons, that's the outer electrons, they come in pairs and they repel each other. So that repulsion is going to force the molecule into specific shapes. And one of those angles that we're really going to need to know is this tetrahedral angle. It's 109.5 degrees. 109.5 degrees. And we won't be asking you for that number, but as a description of that, it is the furthest apart, four objects can be arranged around a point. 4 objects can be arranged around a point. It's the furthest apart 4 objects can be arranged around a point. And the example molecule in the book was CH4, and I'm going to use several examples and little models to show you what these molecular shapes are as we go through these notes. Okay, so we're going to go ahead and slide over to the top of the next page in your notes packet, and we're going to be completing this entire table up here. Basically everything above hybrid orbitals we're going to cover here, okay? Then we'll get into a little bit of this hybridization down here, but again, we're just going to be looking at this. So this table is made specifically to determine shapes, and if you'll notice, it's bolded every time, but central atom, this is key. You have to understand that we're talking about the central atom of these molecules. When we're trying to figure out the shape of the molecule, we don't care about lone pairs of electrons on an exterior atom. We only care about lone pairs of electrons on the central atom, or the number of bonds around the central atom. So it's always, always, always based on the middle atom of the molecule. Now, in order to have a middle atom, you have to have at least 2 things attached to it. So that's where we're going to start. We're going to start with 2 atoms bonded to that central atom. And no lone pairs, 0 lone pairs on the central atom. We're just going to keep it really simple, okay? So I'm going to just draw out a tiny example of what that might look like on a piece of paper. And so you don't necessarily have to draw this in your notes, but if we have 2 atoms, so if I have X in the middle and it's attached to 2 Y's, and it doesn't have any lone pairs, it might look like that, okay? It doesn't matter if these are single bonds or double bonds, or if one of them's a single bond and one of them's a double bond, or it does that part doesn't matter. What we have is two bonded things to our central atom, and there's no lone pairs on that central atom. So that's an example of what maybe your structure could look like, okay? All right, so the total clouds of electrons around the central atom. Well, I have a double bond here. That's one cloud of electrons being shared, okay? It doesn't matter that there's 4 electrons being shared here, but it's a single cloud of electrons. It just has 4 electrons in it, okay? And then there's another section of another electron cloud over on this side of X. So total, I only have 2 areas of electrons around my central atom because there's no lone pairs on X, so I just have those 2. So 2 total clouds of electrons. Now remember, electrons are all negative, so they repel each other. And the furthest apart that 2 things can get from each other is a straight line, okay? So our molecule shape, the shape of the molecule, is going to be linear. Linear molecule, okay? And we can draw a little ball and stick model of a linear molecule by doing 3 ball shapes in a row and then connecting them with sticks to be the bonds, okay? Again, it doesn't matter that that's a single line versus a double bond, doesn't matter. But this is the straight line drawing of a molecule. So I'm going to show you how to draw these on paper if you're trying to draw a shape, okay? All right, now let's make it just a little bit more complicated. I'm going to stick with the 2 atoms attached to my central atom, but instead of having no lone pairs, I'm going to either have 1 lone pair or maybe 2 lone pairs on my X if I had a single bond on each side, for example. Okay, so 1 or 2 lone pairs on the central atom. Okay, now let me draw these both out one more time, but separate from each other. Okay, so this would be one example. So that has 1 lone pair versus this one has 2 lone pairs in the picture, okay? Now again, remember we told you it doesn't really matter if you're arranging your atoms, it doesn't really matter which side you put the Y's on. So if you had like Y, Y right here, and then lone pairs were on, if I had Y, Y, lone pair, that would be the same structure in general because X is in the middle and it's bonded to 2 Y's, etc. So it's okay if it doesn't look like it's a straight molecule on paper, okay? But we're going to learn how to figure out its shape. So in this case, I have 2 bonds and I have a lone pair of electrons, right? So I have a bond, a lone pair, and a bond. That's 3 total areas of electrons, okay? In this one, though, I have bond, lone pair, bond, lone pair. So 1, 2, 3, 4 areas have electrons around that X central atom. Okay, so 3 or 4 areas of electrons. Now remember, electrons repel each other. So this is not going to be the shape of my molecule. Remember, these structures on paper do not show you molecular shape. They don't show you molecular shape. So what happens if you think back to your geometry class? If 3 things are going to get as far apart as possible around X, they're each going to be 120 degrees apart. Okay, and again, we don't really care that you know those angles, but if you were to draw that shape, that angle, okay, it would be like this. This one right here would be like this. So let me explain how this model works. So these are 120 degree angles, okay? I've got Y, if this is my molecule, Y is here, and then the middle is represented by X, okay? And then this stick pointing off is a 3rd set of electrons, right? Electrons, electrons, electrons. These electrons are being shared, that's a bond. These electrons are being shared, that's a bond. But since there's no atom up at the top here, this is a lone pair of electrons. And so this is what the molecule's electrons would do. But electrons are moving so fast we definitely can't see them. And so we can't really see this lone pair of electrons. When we look at a molecule, we can see the atoms that are attached to each other. And so we get this little kind of inverted V shape, the way that I have it, or if I turn it this way or this way, it looks like a V, right? But this shape in chemistry is called bent. So this molecular geometry is going to be bent. Okay? Now, let me show you how this one does the same thing, because this one has two lone pairs. So you might be thinking, well, this pair and this pair are just going to keep them linear. But remember that tetrahedral angle. This is really important. When you have four things that need to be arranged around a point, they're going to be this far apart, 109.5. You have to think three-dimensionally, okay? So it's not 90 because we can go 3 dimensions. Just give me a second, okay? We get 3 dimensions and we end up with something that has 109.5 degrees instead of 90 degrees between everything, okay? So now remember, these two red circles balls would represent the Y atoms. The center part is going to be at my X. And then these two black sticks that are pointing out that don't have an atom on the end, those are going to be the lone pairs of electrons. So these two lone pairs on X. So if I hold it in this orientation, it looks kind of like my picture. My Y's are pointing to the right and left, and my lone pairs are pointing up and down. It's just that my lone pairs are pointing slightly towards me, and my Y's are pointing slightly away from me, right? So again, we can't see these lone pairs because they don't have anything attached to them. If we were to use an electron microscope, we would just see the two atoms on the outside and the atom in the middle and the angle between them. And so we get another bent shape. Now this bent shape, the angle is 109.5. This one, if you remember, had 120 degrees, but either way, it's bent. So to draw a bent molecule, you would have one ball a little bit higher in plane than the other two, and you would just connect them as such. Okay, so that would be how you would draw a bent structure on paper. And just maybe to remind yourself, it would need to have a lone pair of electrons up here in order to make that bent shape. Okay, making it more complicated. Let's go. So here, let's go 3 atoms bound to the central atom, 3 atoms, and 0 lone pairs. So we'll keep it more simple. Okay, I'm going to go ahead and fold those over so we're not looking at them. Okay, so now I have X is still my central atom. I have Y, Y, Y attached to my X, and no lone pairs on X. So all together around X, I have bond, bond, bond. That's 3 different areas that have electrons. That's 3 electron clouds. Thinking back up here when we had 3 electron clouds, that created what we called that created the angle of 120 degrees, right? So 3 things as far apart as possible is going to be 120 degrees away from each other, okay? So here is my model for it now, okay? So I've got X in the middle, I've got Y, Y, Y out here. The farthest apart those 3 things can get is 120. Now, if you look at this model, it is very flat. It's all in one plane, and it's a triangle shape, right? So here is the name of this shape. This is called trigonal. Whoops, I forgot the R. Trigonal, there's T-R-I-G. Trigonal planar. Trigonal planar. Remember, trigonal is triangular, planar is in a plane, okay? To draw that one, you would have a dot in the middle, 3 dots around the outside that are all, as best as you can, 120 apart. Okay, and then draw your lines to connect them. So that's how we would draw a trigonal planar. Okay, still 3 atoms, but now we're going to go ahead and put 1 lone pair on the outside. Okay, so we might have a picture that looks like this somewhere in our shapes lab. Okay, so when we get to 3 atoms all on the outside and 1 lone pair, we're going to end up with, again, 4 areas of electrons. We've got bond, 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 lone pair. That's 4 different areas of electrons. Well, what's the farthest apart 4 things can get? Hopefully you're thinking to yourself 109.5 degrees or the tetrahedral angle. Okay, and so this is an example, and I know this has 3 different colors, but we could have Y, Z, A, or whatever. But so these 3 could all be Y's in this case. X is in the middle, and there's my lone pair. Okay. Now, those three y's want to be as far apart as possible. They want to be 120 degrees, but this lone pair is going to repel those bonds, which means it's going to push those bonds a little bit closer to each other. So while those three are still in the same plane as each other, if I turn it this way, you can see this a little bit. Those three are still in the same plane, but my middle atom is a little bit higher than that plane. So instead of a flat triangle, I now have a pyramid. Remember, we can't see this up here, but I have like a slight pyramid going on. I have my x in a different plane from my y's, okay? So this is trigonal pyramid. Trigonal pyramid. Okay, again, trigonal is triangular, three things attached to the central atom. Pyramid is because that lone pair bends it into a pyramid. It pushes those three away and forces them out of the plane of X. Okay, drawing this one gets a little bit trickier. We're going to do some three-dimensional drawing. So we're going to put the top atom, our X, at the top, okay? And then I'm going to put one of my Y's down here, sticking out in the same plane here. And now here's how we're going to show, so I'm trying to kind of get this perspective, right? So I have my green atom drawn already. It's just sticking right there. But if you look, my blue one is forcing into the page, and my white one is coming out of the page. And there is a way to draw that in chemistry. We do a little dashed wedge like this. So it's kind of getting whiter as it goes down. I didn't do the greatest job there. And that would be the blue one going into the page. And then we do kind of a filled in wedge, color it in, and this is coming out of the page towards you. Okay, so that's a trigonal pyramid. Okay, then our final shape for this class, you'll get more if you take college chem, but our final shape for this class is four things around the central atom, 0 lone pairs. So if you have four things around X, just fold it one more time so that we can focus on what we're doing. You have X with 4 Y's around it. Okay, 4 areas of electrons, no lone pairs, so we're just at 4. What's the farthest apart 4 things can get? Well, that's the tetrahedral angle again, and I'm just going to go ahead and use the one that I was working with before, but if we look at this one, this is the tetrahedral angle now with everything visible because all ends actually have an atom on them. So this is a tetrahedral shape. Okay, so the shape of the molecule is a tetrahedral. Okay, and to draw this one, okay, here's how I'm going to try to draw this one. I'm going to keep the blue atoms in the same plane as X. Okay, so I'm going to have an atom at the top bonded to X in the middle, and then another atom out here. Those are all in the same plane. So blue, X, and blue all in the same plane. Now what's left is I have the green atom poking out of the page, the white atom poking into the page, and so that's how we're going to get this one. Again, a fat wedge colored in is poking out of the page. A wedge that is dashed like that is into the page. Okay, so that's what a tetrahedral looks like. Oh, also up here, I'm going to just go ahead and add a lone pair of electrons on that trigonal pyramid to explain why this is a pyramid instead of a flat triangle like that one. Okay, couple of other hints. 2 atoms will always form a linear molecule. Okay, and here's an example of that. If you have 2 atoms, it doesn't really matter how you put them together. They are forming a line with each other. So the ball and stick for 2 atoms is just literally 2 with a dash in between. Okay? All right, lone pairs bend molecules. Lone pairs bend molecules. So if we look up here, there's no lone pair on this linear molecule, so it's straight. But you add a lone pair and you get a bent molecule because this pair pushes those 2 bonds closer to each other. Same thing here. Trigonal planar, no lone pair, so it's nice and flat, planar. But you add a lone pair to the middle and it bends the molecule into a pyramid. So lone pairs bend molecules, so that's where we get bent and trigonal pyramid because they're not flat or straight when you add that lone pair. Okay, and then finally, symmetry. What I want you to do is I want you to put an asterisk next to linear, trigonal planar, and tetrahedral. And then down here for symmetry, I want you to put these shapes can be symmetrical if, and this is a big if, all outer elements are the same. If all outer elements are the same. Okay. All right, last little bit here. And so this is what you need in order to do your shapes lab. And there's a little bit of a tutorial video in Canvas to help you with that shapes lab for columns 3 and 4. But we're going to talk about hybridization. Now, hopefully you've heard the word hybrid before, especially with like vehicles. A hybrid vehicle is a mixture of gas and electric. That's literally what hybridization means. It means mixing. So why does hybridization occur? Well, hybridization of orbitals is mixing orbitals, okay? So orbitals mix to create better bond angles, for electrons to spread apart as far as possible. For electrons to spread apart as far as possible. And to create more overlap in the bonds. So that makes those bonds a little bit stronger. Again, if you end up taking college chemistry or AP chemistry, you're going to get into that sort of detail in much, much more detail, which is awesome. But that for now, we just need you to know hybridization is orbitals mixing, and they do that to get better bond angles, makes the electrons spread out more, but also gives better overlap, which makes those bonds stronger. Thanks for tuning in, and we will see you in class. Make sure that you email us if you have any questions, okay?